Recording out there, I did it. Okay.
I didn't know you were going to have so many syllables in the title.
Right.
Wow.
How about that?
That's pretty impressive.
Well, if you can read it, wait.
Okay, well, let's get started in the interest of time now that Mike's here. We are fortunate to have with us Dr. Paul Metz. Dr. Metz has been with us several times, so I'm just going to read the first paragraph of this bio. Dr. Metz is a PhD, a DIC, a CPG, a PG. He is a professor of geology engineering with UAF College of Engineering and Mines and licensed professional geologist and president director of Fairbanks Exploration, Inc. As a longtime resident instructor, Dr. Metz has extensive knowledge in geological economics and Alaska energy issues and has a deep interest in expanding resource development and opportunity generally in Alaska and the interior. So that kind of boils down in economic development terms to diversification of our economy. Bud talked about that, but it was in, when he was speaking, but it was kind of in relation to 1920. Not much has happened. All the floor is yours.
Comparison.
All right. Well, you can all see the title here of this presentation. It's based on a review of scientific literature, and there's a short bibliography of some pertinent literature that's available in the Rasmussen Library here in Fairbanks. So you don't have to go filed to a major Australian university, but he had a long career in the resource industries. He was the chair of the Department of Earth and Planetary Sciences at Adelaide University, and he is a twice recipient of the highest scientific award given in Australia for his research in the whole spectrum of the earth sciences and planetary sciences, earth and planetary sciences. The other little reference there by Kirsten Peters, she did her undergraduate work at Princeton and Harvard, received her PhD from Harvard, I believe, or right the way around. She's written this popularized little volume, The Whole Story of Climate Science. And it's a really, really good short discussion, much less detailed. Plimer's volume has about 2,300 refereed journal articles that he's compiled for. And I'm going to go through each one of those. So I hope you guys brought your lunch and your dinner with you.
Cool.
This is just the general outline again, using his and all of the figures that you're going to see here, except for two, come from his 2009 publication. He also was the author of a 5-volume series on Encyclopedia of the Earth Sciences. It was published by Oxford University Press a few years ago. He's written about 120 refereed journal articles. So first thing I want to do is differentiate between weather and climate. Weather is the short-term, local, and limited aerial extent of the temperature, moisture content, atmospheric pressures, wind velocities, directions, and the degrees of visibility, where climate is the long-term, and what is long-term and short-term is varies. The Germans consider the minimum time period for differentiating between climate and weather 30 years. Generally, our climate forecasts are for a few days and up to 10 days. But our weather, as well as our climate, is a chaotic process. In other words, after about 10 days, it doesn't make much difference what you start off with in terms of the critical parameters of temperature and water content and barometric pressure in the atmosphere. You're going to get a different result, even if you have the same, nearly identical boundary conditions to start off with. And that's what makes it so difficult to predict the weather, and nearly impossible to predict what's going to happen much more than 10 days out in the future. And so these general circulation models that are trying to predict the climate out for 100 years based on a single parameter. In economics, we talk about holding all of the other variables constant and changing one of those variables to determine what's going to happen to the economy. We can't do that in climate science. All the other variables have to be taken into consideration. And because of that, we have a very complex and chaotic system. So the essence of science is observation, measurement, and experiment. And essentially, what we're seeing with the discussion with respect to anthropogenic climate change is based on computer models. And one can devise a model to generate information or output based on the assumptions and the input parameters of that model. And so we can design computers to come to a conclusion if we so desire. When you play a little video game, how many of you, when you were younger, played Mario Brothers little video games? Yeah, and so when you go through the iteration and you fail, you push the reset button and you start all over again. And so we got to remember that all of these projections are based primarily on models, and if you ignore the measurements, the primary sources of information, or the primary science that is behind those measurements, then you're going to come up with a different answer. So we differentiate between a scientific theory and a hypothesis. We develop a hypothesis concerning some observation or concept that we have developed, and we test the data that is available and seek new available data, and then try to prove the validity of the hypothesis. The key is that one contrary piece of evidence then can result in a rejection of that hypothesis, and with that, the necessity to develop a new hypothesis or find other frameworks in which to state the concept. So the important thing is here, one piece of contradictory evidence is going to reject the hypothesis. Keep that in mind. And what I want you to do is tabulate how many contrary pieces of evidence we present here with respect to this anthropogenic climate change hypothesis. So, yeah. Latin proverb here, where there is doubt, there's freedom, and the next is my discussion about that. And the bottom line is, we're only going to come up with the correct answer if we ask the correct question. And so much of what has been discussed in the public forum has been to limit the testing of the hypotheses, the counter hypotheses, and with that, the absolute antithesis of science. Science is about doubt, not about dogma. So, back to the introduction of this issue of general circulation models. This is some 5 different general circulation models that were run on a period from 2000 and projecting out to 2025. And then you can see the actual there refers to the actual temperatures that were measured, and the reality is the CO2 measurements that were made of the atmosphere in 2008. And you can see how much the actual data diverged from the computer models even after only 8 years, let alone 100 years.
I'm confused. Where is this measurement taken?
These are measurements that were taken all over the globe. Satellite, the measurements of temperature were satellite measurements. The CO2 estimates were taken at multiple stations on the globe. So, climate change. The climate's been changing for nearly the entire history of the Earth, in which we actually had an atmosphere, but we're really generally concerned with the changes, and we have good evidence of those changes for about the last 450,000 years, from ice cores in Antarctica and Greenland. And we can go back about 600 million years with respect to other measurements of oxygen and carbon isotopes, and other evidence with respect to proxy evidence with respect to the climate. So you can see in the Pleistocene, for the last ice advance in the Pleistocene ended about 14,700 years before the present, BP before present. It was the last of the ice advances in the last 2.6 million years was the most severe, but it was not anywhere near as severe as the ice advance in the late Phanerozoic about 1 billion years ago. That one almost resulted in a permanent snowball Earth. And there were at least two major glaciations before there were complex life forms. The period of complex life forms, and we'll see some diagrams of that, is from about 600 million years ago to the present. And we'll see why that's important again. But you notice here in this chart, a cooling period, the Pleistocene Wisconsin ice advance, ending 14,000 plus years ago, and then the Wuling warming period, and then the older Dryas, another cooling period, the Ellerod warming period, younger Dryas, cooling period, and on to the modern warming period that we've had since 1850 AD. So we've seen significant climate change that we can measure in the field, observing the glacial deposits and dating the ages of those glacial deposits using radiogenic isotopes. And measuring the oxygen isotopes. Oxygen has 3 stable isotopes, oxygen 16, which is the most abundant. We're talking about oxygen and atomic weight, which we use as oxygen 16. So there's 2 heavier isotopes, oxygen 17 and oxygen 18. And by looking at the ratios of oxygen 16 to 18, we can make some proxy estimates to temperature. That heavier O18 is not mobilized as readily as oxygen 16. You can think about it as having two billiard balls, one made out of foam and another one made out of ceramic, and with the difference in momentum. And so in the evaporative process, or in the process of concentration of life forms, the isotopes can be separated naturally. And so we measured those samples of those separated isotopes to estimate temperatures of the materials, or the environment that those materials existed in. So here we look at temperature variations measured. In this case, the heavy line is compilations by the University of Alabama of global surface thermometer measurements, and the MSU satellite data is satellite data. And then the CO2 measurements, again, are global measurements. And you can see this dotted line is continuing to increase up to about 385 ppm in 2009. At the same time, the global temperature measurements have diverged in about 2006 and decreased for the last 3 years. So here, again, there's not a one-to-one correlation between CO2 and global temperatures. So keep in mind that 385 ppm. Pre-industrial was about 100 ppm lower than that. We'll talk about that some more in the future. So history. The speed and amount of modern climate change unprecedented? No. Is dangerous warming occurring? And we can say unequivocally, the evidence that you're going to see here, no. Is the temperature range in the 20th century out of the range of normal variability? And again, you'll see that the answer to that is no. Here is some proxy temperature measurements for the end of the Wisconsin, the Pleistocene Wisconsin ice advance that ended, as I mentioned earlier, about almost 15,000 years ago. And you can see to your left how erratic the temperatures were through the previous roughly 27,000 years, and how the temperature varied much less as the ice age waned. So the general circulation models predict erratic weather conditions during periods of warming, where the measurements that we make, temperature measurements that are made today and the temperature measurements that are made by proxy, by oxygen isotopes, show just the opposite. So we have a huge contradiction with respect to climate variability. Climate is a function of both temperature and precipitation, and oftentimes we forget that. We could do the same exercise looking at the variability of precipitation here in Fairbanks by simply looking at a topographic map of the Goldstream Valley and looking at the meander curves that were formed in Goldstream Valley early on, some 60,000 years ago, and compare those to the meander curves that are entrenched along those longer wavelength curves. And we can demonstrate that during that little warming period of the last Wisconsin ice age, the precipitation in Fairbanks was about 15 times greater during that cold period than it is today. So precipitation was much more erratic then, as well as temperature. Here again, we see 100,000 years of temperature data, and again, on the very far left, at about 10,000 years ago, 10 to 15,000 years ago, you see this dramatic warming and a decrease in the permeable value of oxygen 18. And you see again, much more stable temperatures during that last 15,000 years as compared to the previous 85,000 years. There's also a misconception that global warming will cause desertification. There is abundant evidence that we've known long before this debate that most of the deserts of the world today originated in the Pleistocene during the last major ice age. And this is an attempt to reconstruct the extent of the rainforest today versus how much it contracted during the Pleistocene. And it's when a very large portion of the precipitation falls as snow and is accumulated as ice sheets on the continent, then there is less precipitation in other parts of the globe. And the colder temperatures result in less evaporation. So it's consistent with what we know about the hydrologic cycle, that desertification should take place during cold periods. This is a diagram showing that the dark is the extent of the continental ice sheets 20,000 years before present, which was the absolute maximum. It was a really cold place here, about 60, minus 60 temperatures, and probably in the interior here. And you can see the continental ice sheet in North America extended further south than the Great Lakes. The terminal moraines of the Wisconsin Advance are in northern Indiana, northern Ohio, and northern Illinois, and the very western part of southern Wisconsin.
The gray versus black over Alaska there, is that the Tanana Valley?
Yeah, that is
that interface?
Yeah, exactly. If we drive to the Canadian border, when we get to the border, that's where the ice stopped. It didn't have a passport. And so there's the Tintina Trench was actually, or I should say the portion of the Tintina Trench in Alaska was ice-free during the Pleistocene.
Mike, where are you talking about? Can you point it out on the map?
Yeah, it's this one, this right here. This
Oh,
finger that sticks
okay, yeah.
So, and another time interval here, looking at the changes in the very, very end of the Pleistocene, seeing the relationship between the temperature and ice accumulations. Now, this caused a huge controversy. Several Canadians wrote an article, and they compiled data and did some statistical manipulation of the data, and produced this upper chart for the the temperature anomaly between 1960 and 1990. The interagency panel on climate change jumped on this, and this became their mantra for anthropogenic climate change. And some other doubting Canadians did an alternate compilation and produced the graph you see at the bottom. And there you see from 900 to about 1500 AD, or this dark bulge. That's the medieval warming period that you saw on that initial chart previously. That's well documented even with respect to historic records, let alone to anthropological and geologic data. And then to the right of that is the Little Ice Age that began around 1500 and continued on until about 1850 or so. And there were a few warming periods in the Little Ice Age, and then the very end there at 2000 is our current temperature maximum, and you can see that is actually a couple of degrees cooler than the medieval warm period here. So,
what would that look like if you actually put the extra 20 years? Because we're in 2019.
it would actually, well, you saw this big drop since 2008. You would see a continued rise until about 2008, then a dip. So the sun, in all this discussion, poor Mr. Sun is often left out, but the sun is the driving mechanism for our climate, not 1/1000th of 1% of CO2 in the atmosphere. The sun drives the hydrologic cycle, provides the thermal forcing that heats the earth, and it also influences the orientation of our planet Earth, and so it is the primary driving mechanism for our climate. And unfortunately, we don't know a lot about the sun. We know in the short term some of the regular cycles, which we'll talk about. And this one is the one that you've all been able to observe yourselves, the aurora, the sunspots, and the consequent aurora borealis. And you can see the relationship between sunspot activity in the irradiance of the sun. And these sunspot cycles vary from about slightly less than 10 years to about 13 years. The problem is we don't know a lot about the longer term cycles of the sun, and then when we have these very large irregular events, those have an even larger impact on the climate.
And you circled 21, 22, 23.
Those are, though I didn't, these are the people began collecting data on sunspot cycles. And so these are cycles 21, 22, 23 since the beginning of the process.
Okay.
And they're often referred to in the literature to relate the temperature data to a particular cycle. Here again is a graph showing the relationship between the cycle length as I said, they range from about 10 years on up to about 13. And there is a very strong correlation between the temperature anomaly and the sunspot, the length of the sunspot cycles, as you see here in this graph. And then the bottom line there, the CO2 concentration, it doesn't appear to be related to either the temperature or the sunspot cycles. And we'll see that again over a longer time period.
Can you go back to that just 1 second? Just seems to be inversed.
Yeah, as the cycles are shorter, there's more intensity of the radiation, irradiation.
Oh,
So, do volcanoes change the climate? Yes. You know, and we have recent evidence for that. The eruptions in your lifetime and in the Philippines and Mexico, and more recent one in Iceland, all resulted in decreasing temperatures as a function of the ash that was put in the atmosphere. Dramatic one with respect to Krakatoa, and that resulted in winter, winter all summer in New
Almost
England.
2 years.
Yeah, exactly. And as far as impacts on life forms, yes, there has been past climate events that have resulted in extinctions, and there's others that have not. Okay, here again is this proxy, oxygen isotope proxies. These curves are developed by thousands and thousands of oxygen isotope measurements. Now, it's incredibly tedious work. I spent a year at the British Geologic Survey Isotope Laboratory when I was doing my PhD measuring stable isotopes. And so I really appreciate how much science and effort has gone into all this data compilation. But what you see here is an averaging of those temperature peaks and troughs, and you can see at those troughs in the Ordovician-Silurian boundary, about 450 million years ago, there was a major ice age, and again at the Carboniferous Permian. The Permian was a really strange period. It had a glacial age at the beginning, and at the end it was the hottest period in the history of the Earth since complex life forms developed 540 million years ago. And then another ice age in the Jurassic and early Cretaceous, and then again the Cretaceous is a very warm, ended as a very warm period. And then from the peak, the thermal peak of the Cretaceous, then it's been downhill with respect to temperature ever since. So the last 70 million years has been marked by a continuous decline in the climate of the Earth. Now, in addition to the oxygen isotopes being significant with respect to temperatures, we can make inferences with respect to the CO2 in the atmosphere, both with the carbon and oxygen and deuterium isotopes. We can make projections of both CO2 concentrations and temperatures. So in this one, this real gray area is the error bars plotted for the estimates of CO2 in the atmosphere. There were multiple compilations. In this one, it's the Royer compilation. There's a more extensive one that was done and published in the Journal of Geophysical Research. Again, before this climate change debate really got heated. And in this diagram, the CO2 has been normalized, CO2 concentrations have been normalized, or should have been normalized to the current concentrations of about 285 to 385 parts per million. And it doesn't show that readily here, but these are the normalization multiples. So in the Ordovician Silurian boundary here, we're seeing the CO2 concentrations in the atmosphere are about 15 times. 15 times, not twice, but 15 times what they are today. And yet there was a major ice age developed at that period of extreme CO2 concentrations. If we go back here into the Precambrian, you see that those concentrations are higher yet. And that's when the largest of the ice ages occurred in the late Proterozoic. Huge contradiction with respect to this anthropogenic CO2 emissions and climate change.
It doesn't have to match up with, either asteroid strike supposedly or volcano that would have caused cooling despite the chemical mix-up of the atmosphere.
This is a very long trend event. How long does a volcano last? How long does an asteroid impact last? Those are at the time current what are called RCCEs, recent climate change events, or recent extreme climate change events. Those irregular ones that spark some dramatic climate change, like Krakatoa. They're long-term trends. So these are the extinctions, and this was a compilation of terrestrial extinctions. There weren't terrestrial life forms until about the Devonian. So you see here the extinctions are only from 400. Well, it's about 350 million years ago to the present. There were extinctions before that. There were extinctions in the Cambrian and some in the Ordovician Silurian as well. But what you see here in this period from the late Cretaceous on, a huge increase in the biodiversity of the planet. And it probably was in response to, what did I say earlier? The peak of the temperature optimum in the Cretaceous. That was since that peak, it's been global cooling. So this biodiversion has taken place in a time of cold global cooling rather than.
There's a book title, which I haven't read, but it's called The Sixth Mass Extinction. Is that what this number 6 is?
Yeah, there was a late Miocene, but you can see that it's only 2% of the extinctions that took place over that. What they're referring to is, no, what they're referring to in the 6th extinction is man. It's humans, the planet without us. So there's lots of proxies that we've had with respect to temperatures. But when we look at ice, glacial ice, we can actually see distinct layers in which we can relate to a particular time interval. And the deep ice cores in Antarctica really provided the best information with respect to climate change by measuring the CO2 in those little bubbles in the ice We can estimate the CO2 concentrations and the temperatures. And this has been done, the deepest cores there were provided us with a little more information about the last 440,000 years. Didn't cover all of the Pleistocene because the earlier glaciers had come and gone, and they're no longer represented.
Paul, I've got a question on that in Antarctica. Is there a correlation between the ice cores in Antarctica and Greenland, for example?
Yeah,
There is a correlation.
yeah, there is. You can see that similar pattern. Dust contents are a little different, but the CO2 and the temperature data is very similar. But so what you see is if we go back in time, here we are today in this warming period, and again you can see for the short period of the ice core data, relatively stable temperatures based again on the direct measurements of those oxygen and carbon isotopes. And then as we move back in time, we see this cooler period, and each of these periods of gradual cooling and then a rapid spike and a great warming period, and then another period of global cooling, and then a spike in global warming. So we see that same pattern here for all four of these 110,000 year cycles. The current global cooling and the global warming is nearly identical, and the exception that these two were actually higher temperature peaks than what we've had today. So when you hear the news and it says, yesterday was the hottest day since we've been keeping climate records, what they're talking about is the little thermometer that's out there next to the runway or in downtown LA, rather than what has occurred over the period of time that we actually have scientific data for. It's a tremendous misrepresentation of what has occurred over the current warming period, let alone over the last 440,000 years that we actually have data for. So in addition to this pattern of temperature change, we see this pattern of CO2 concentrations. And if you look closely at this, and we'll look at it even closer and a little much narrower. So we had this rapid period of warming, and then we had an increase in CO2 content. So is CO2 driving this temperature range, or is it following this temperature range? From this graph, it appears to be following. And the other thing that's important is in this graph, in these little bubbles, we can also measure the dust, the accumulation. So we can see the effect of not only temperature, but the wind conditions. And Jim, when he flies his airplane in front of a major glacier in the summertime, can attest that when the continent was covered with ice, it was a really damn windy place. And if we look out the window here, we can see meters and meters of windblown silt. And if we go to China, we can see 600 meters of windblown silt. It was not a nice place to live during the Pleistocene. It was windy and it was dusty. And these are all indications that those extreme wind events that occurred at the bottom, at the coldest time periods, because there were great thermal gradients between the ice sheet and the ice-free areas. Well, I said earlier that it's the sun that drives the climate. It does, but what we can see in the geologic record shows that there's some periodicity. And it's not the periodicity of the sun, but it's the periodicity of the Earth relative to the sun that is important. Back in the 1860s, a Scottish janitor went to work in a Scottish university, and at night he went into the library and read and became self-taught. And he began to write articles in British journals based on his observations and his literature searches. And he came up with the hypothesis that it's the changes in the Earth's orbit that affect the amount of thermal radiation that impinges on the Earth. And that's what produces these long-term cycles that we call ice ages over 100,000 year intervals. And there are three motions there that are important. The Earth's orbit around the sun is not a spherical orbit, it's a slightly elliptical orbit. And that changes over time. It changes as a function of the position with respect to the other planets. So when the ellipse is very extreme here, and the Earth is over here and the sun is here, it's very far from, it's farther from the sun, and with that, less energy impinges on the Earth. The other variable, and so over time, this ellipticity changes from nearly spherical to its extreme. And that's about 110,000 year cycle. Two others that are important. The Earth's axis is tilted between 21 and 24 degrees to the axis of rotation. The axis of rotation is tilted with respect to the ellipse. And so as the Earth is tipped away from the sun, the northern hemisphere receives less radiation than the equator, and the southern hemisphere receives more. Mm-hmm. And when the axis is tipped towards the sun, the northern hemisphere, it's reversed. Okay. Well, there's a cycle of about 40,000 years, 41,000 years from the change of that, from 21 to 24. And that greatly changes the amount of energy that is pinched on the Earth. There's a third cycle, and this one's a little more complicated to envision. But today, the Earth's axis is on the 21st of December, it's pointed away from the sun. But we are at the closest point distance of the Earth away from the sun. So we're at that elliptical minimum. And so there's a countervailing, we're getting less solar radiation on the 21st of December because we're tilted away, but we're getting more than we would if we were further out in the long axis of the ellipse. Mm-hmm. And so that is about a 23,000 year cycle, 21 to 23,000. And so when we combine all of these, there are significant changes in the solar forcing, the amount of energy that hits a particular spot on the Earth. And so this is what the solar forcing, the model here is showing at 65 degree north, what it would be with an overlapping of each of these periodicities. So you can see there's some dramatic changes in the amount of energy as we go through this, in this case, a full 4 200,000 year cycle, 100,000 year cycle here, and a full 1,000 billion years. So these cycles fit very well with respect to the measured data that we talked about earlier, the oxygen isotopes and the temperature estimates for each of these cooling and warming events.
So you get down to the graph that shows stages of glaciation, that is backed up with.
Yeah, this cooling event, this would be the onset of a glacial period here, and the low point would be the back to the extent of the glacial, and then this peak jumps up very rapidly. Now, the question is, what causes that rapid climate change? And this occurs based on the ice core data that we have, it can occur over incredibly short periods of time, a few years or a few tens of years. So it's very rapid climate change. You can see how much difference there is between the low and the top. And that has been a conundrum of what drives that. And when I was working on my dissertation, I wasn't doing climate change. I was measuring CO2 in rocks. And CO2 and methane are gases that, when you cool them under pressure, will form what looks like ice.
Looks like what?
Ice, and it's called, the technical term for that is a clathrate. We have huge amounts of clathrate, class rates of methane on the North Slope.
Mm-hmm. Would you pronounce that again?
Clathrates.
Spell it for me. I can't hear that well.
It's CLATHRAT. And these, in the case of CO2, under pressure, the CO2 will disassociate that clathrate about 31 degrees C. So it's way above the freezing point of water. And methane is even more sensitive to changes in pressure. And other people have been thinking about this as well, and it's probably when we draw down the hydrostatic pressure of the oceans, as we put all this water onto the continental ice sheets, we change the pressure regime, and the pressure is hydrostatic. So over the entire globe, when you hit a particular level, that may have been susceptible to more clathrate formation. The clathrates disassociate as a function of both temperature and pressure, but also salinity. And so you can disassociate them by putting more salt in the water. And so I think what probably happens here is we draw down to a point, and then we get methane hydrate disassociation very, very quickly. And it all at once, essentially.
Is that happening now?
Yeah. And I think there's a lot of, we don't see it on a large scale, but once in a while we see these really strange bubbles that occur in the ocean, particularly in the Caribbean. And there's been a long history of shipwrecks in the Bahamas in particular. And there's huge gas deposits in the Caribbean, and these huge amounts of clathrates. And it's probably when there's slight changes in the sea level or changes in the salinity of the bottom currents, those clathrates disassociate, and when they do, they bubble up, and with that, the buoyancy of the water decreases, and ship that's over top of that bubble will sink. And that's probably why we do these major shipwrecks that occur.
The Devil's Triangle.
Exactly, the Devil's Triangle.
Well, question, it seems to me that, if overall temperature is down for a period of time in a year where snowfall and that will accumulate, will increase.
Yeah.
However, even if temperature doesn't go down, if you just have conditions that result in heavier snowfall, that would also increase glaciers. So is glacier buildup and decline, particular glacier buildup, always associated directly with temperature change, or is there something?
Well, yeah, temperature affects the hydrologic cycle in the amount of evaporation that takes place. Colder temperatures, evaporation doesn't take place near as rapidly as it does in warmer periods. But don't forget, this is a huge, the folks at the equator, they're getting the same amount of solar forcing, whether you're tilted at 21 degrees or 24 degrees. So we have this huge temperature differential between the poles, and so what is key here is the transfer of that heat from the equator to the polar regions. That then affects the wind as well as the precipitation, the evaporation, and the precipitation in the polar regions. So here we can see the last 6 million years here of the Earth's history. The cooling that's taken place, as I mentioned, began as early as the very latest Cretaceous, and then continued on through the entire Tertiary. But then we see significant ice builds up about 4 million years ago in Antarctica, but there's actually smaller alpine glaciers and smaller ice sheets that started about much earlier than about 14 million years ago. And then during the Pleistocene, this much more erratic climate as a function of the climate cooling. So known cycles, tectonic ones, highly variable. Those probably influenced some of those early ice ages in the Proterozoic, and started seeing plate tectonics begin on not in just the Phanerozoic, but even before that in the Precambrian. These are highly variable. We've done reconstructions of those plate boundaries, but it's much more difficult to have precise estimates of what occurred when. There's some very large long-term cycles again associated with the rest of our solar system, but the ones that are really significant in the near term are these orbitals that I talked about, and then these 1,500-year cycles, and then some shorter cycles that are a function of the sun. And again, we don't have as much data for those as we do the orbital. And then finally the 10 to 13 year cycles and the sunspots. We're seeing both melting and addition, and if you looked at the internet this morning, you see one of the largest glacier in Greenland has kind of come to a screeching halt. In this last year, it was moving fairly rapidly and producing a lot of large icebergs into the North Atlantic, and since 2013 it's slowed down, and it's probably due to circulation of the water in the fjord changed, and with that, the surging glaciers are surging, and it's building up both vertically and horizontally. It's not retreating anymore. So here's again these the glacial cycles and the temperatures, and as I pointed out earlier, the previous global higher climate optimum, the previous advance in the Illinois advances several degrees warmer, and the Canson was even higher than it is today. And this shows the again the CO2 in the atmosphere and the average global temperatures, and those lows all are congruent with the ice ages that I mentioned, the Ordovician Silurian, the Carboniferous Permian, and the Juro-Cretaceous. And as I mentioned just a little bit earlier, that you can see this ice sheets actually, there's evidence that the ice may have began as early as 38 million years ago in Antarctica, and, but it really got major accumulations in the last 15 million years, much later with respect to the northern hemisphere. There is a typo on this one, though. This should say the Eocene rather than the mid-Miocene climate optimum. And again, the same cyclical data that we looked at before, and again, an inference that the CO2 actually follows rather than leads the temperature rise. And you can see it even better in this diagram, particularly here you can see the temperature is rising and CO2 is increasing, but there's a jump here, and it continues, the temperature continues to rise here, and again there's a jump in the CO2 present in the Antarctic ice cores. So all suggesting that rather than driving the climate, the CO2 in the atmosphere is responding to the temperature changes.
Right, love is out, Doc. All of that is true, save the Industrial Revolution. For all of the span you're talking about, or for the great part of the span you're talking about, these were essentially natural functions. It would be chasing. But we have been dedicatedly taking carbon that was encased in a solid inert form and making it aerosol. And so it's not load following anymore. We did it. We've been doing it.
Yeah, there's
so I just do wonder what that interplay is going to be. That's really what we're talking about.
But wait till the last two slides.
Okay.
we got to kind of rush through this because we're running out of time.
Oh, we got time, baby.
We got lots of time.
Okay, again here you see the sea ice constant, and the upper graph is Antarctica. This guy was an Australian, so he puts south above the north. and you can see that there's been fluctuation in sea ice in both Antarctica and Arctic and the Arctic, but a slight decrease in sea ice here in 2005 through 2008, but slight change possibly in southern. Nothing dramatic with respect to sea ice change. So water, we'll jump through these real quick. Problem with estimating sea level change is there's a lot of factors that affect sea level other than the amount of water that is. One of them is the isostatic rebound after the ice sheets have been removed. And here you see the isostatic rebound in Finland. So that area that's been depressed by 2 miles of ice now is rising, so you would get an apparent decrease in the level of the sea as a function of this isostatic rebound.
Oh, wait, darn.
So even though you're adding more water to the ocean, it appears that there's
That
the
was
other-
Florida though.
the other really insignificant thing, and is just as rapid. We know that the Alaska Range is rising at about 1 centimeter a year, and so are other mountain ranges around the world. So plate tectonics on places like the west coast of North America, where there is subduction going on, and like under the Gulf of Alaska, there's very rapid uplift, and that would then suggest that sea level is decreasing, just as the isostatic rebound would indicate. But on places like the east coast of North America and in areas of large deltas of rivers, the sediments are subsiding. And so it would then indicate that there's sea level rise. So trying to come up with a true level of change of sea level is very, very difficult. And at the same time, their plates are moving, so the seabed is changing too. So it's the average, it's the contour of the seabed, as well as the position of the continents that give us this relative sea level. So here, trying to estimate what the sea level was, again, based on ocean sediments and oxygen isotope estimates. We can, this previous ice advance and rapid global warming resulted in about a 7 meter. This is about 7 meters higher than the current. So over 110,000 years, the sea level rose 7 meters, and not several meters in 100 years, like we are projecting from our general circulation models. CO2, there's variable solubility. If you took nothing away from this lecture or this discussion, you should take away that if you want to have the best bottle of beer, keep it capped and keep it cold. That's all this diagram is telling us. There's 6% CO2 in an ocean environment at 0 degrees Fahrenheit and 30 bars of pressure. So the highest concentrations of CO2 in the ocean are at the greatest depths because the temperatures are right close to 0, and even higher pressures than 30 bars. And so this high CO2 concentration is not only in the ocean water, but it gets siphoned through our mid-ocean ridges, and this high concentration of CO2 in that water reacts with those basaltic rocks to form the mineral calcium carbonate. And we see a lot of evidence. This was one of the big debates in geology in the turn of the 20th century, was how come these oceanic basalts that we see from mid-ocean ridges, like we see in Greenland or in the Canary Islands, how come they're so full of calcium carbonate? They have a composition more similar to a granite, but they're obviously a basalt. They're black, and they have the texture of basalt. Well, it's the carbonation of those basalts. And this is what has been suggested as a way of sequestering CO2, man-made sequestration. It's taking place over 14,000 kilometers of the mid-ocean ridge every second. And this does not get included, this natural sequestration doesn't show up in the general circulation models. There's concern about the overturn and the circulation of this warm water from the equator to the poles. That's dependent on temperature gradients. So let's look at the temperature gradients over just the last 35 years or so. And we see these huge fluctuations in ocean water temperatures, which show that there's significant gradients. The gradients haven't diminished significantly. These gradients have remained relatively constant over time. So this concern that our conveyor belt is going to stop because the surface water temperatures are rising, so far there's not an indication of that in the data. What there's indications that there are events, El Nino and volcanic events that result in cooling events associated with the volcanic eruptions and then this warming event. And exactly what the mechanism of the El Ninos is been in question, but it actually could be geothermal rather than atmospheric. That in these mid-ocean ridges, we are heating the water. And there's, as I said earlier, there's 24,000 kilometers of ridges around the globe, spreading centers. And so we're heating a lot of water with those submarine volcanic eruptions. And with that, changing the circulation of the ocean water, and that then impacts the continents as the water moves from west to east in the southern hemisphere in particular. Air, we're going to make this real quick here. Hurricanes that, and these are little diagrams of this solar forcing, shortwave like radiation coming into the atmosphere and in part blocked by cloud cover. And then the heating of the surface of the Earth emitting long wave infrared radiation back into the atmosphere to warm the atmosphere, and then some of that being radiated back into space. And essentially, that has been relatively balanced, and with that, no net increases in temperature or decreases in temperature over long periods of time associated with the greenhouse gas effect. Here we see, and I always ask this question in my geomorphology class, what is the dominant greenhouse gas? Well, it's water vapor. And anybody that goes golfing in Arizona realizes that. In the daytime, it's very, very hot. At night, it's very cold, and it's because there's an absence of water vapor in the atmosphere. If you go golfing in Atlanta, the temperature stays the same all the time because it's so damn humid. It's always uncomfortable.
That's true.
Yeah, that is true. I went to boot camp in the South, and it was terrible. And this is just another diagram showing the same thing. These are satellite measurements of temperature in the recent, from 1980 to 2008. And you can see a slight warming in the northern hemisphere and a slight cooling in the southern hemisphere, and the net for that entire time period, we integrated that. The areas above and areas below, it'd be about zero change globally. Why is that so? Jomo's question. We're putting all this CO2 in the atmosphere. Well, this is where the global warming takes place. That first 20 parts per million, that those little microbes, those little bacteria that began to develop in the early Precambrian, 3.8 billion years ago, they provided enough CO2 over time to heat up the Earth, and as you can see, the amount of absorption decreases as the CO2 concentrations increase. Just like this little glass of water here. If I stick this corner of this there's this little tissue that absorbs all the water. But if I saturate it, it doesn't absorb it anymore. And that's what CO2 is doing. And that by the time we got up to 285,000 parts per, or 285 parts per million, in the pre-industrial period, CO2 is doing its job. It was all done. What after retirement? It doesn't make any difference how much more CO2 we put in the atmosphere. Each additional 20 parts per million has a minuscule effect on the change in the temperature. So get out here.
Did the author address the maximum amount of carbon dioxide that air-breathing mammals, in particular the human, can tolerate throughout this increase in carbon dioxide, if there is an increase?
Well, the point is that it's not going to stay in the atmosphere. It doesn't, and it's going to be recycled.
Well, the point I wanted to make, Paul, is blood chemistry is complex. The blood will only hold so many millimeters of pressure of carbon dioxide, and that's it.
Right.
It doesn't matter how much carbon dioxide is in the atmosphere, the blood will only fill it. When you get too much carbon dioxide in the air, it's not carbon dioxide that's toxic, it's the lack of oxygen that the carbon dioxide displaces. So all this thing about carbon dioxide being toxic to human beings is just pure BS.
Yeah, it is. And it's the relative abundance of carbon and oxygen. Carbon is the 15th most abundant element on the Earth. What's number one? Oxygen.
Oxygen.
And more importantly, I said that the carbon, the CO2 is not going to stay in the atmosphere. The reason it's not, there's a huge driving force. The lowest energy state of carbon is not CO2. When we burn a mole of CO2, we generate about 400 kilojoules of energy. But there is still the potential for another 60 to 180 kilojoules of energy. And so what does that mean? CO2 is going to make carbonate. It's going to do it somehow, someplace, and it's going to be relatively quick. Our CO2 cycle in the atmosphere is measured in a few tens of years at most, generally less than that. And methane is much shorter. Methane is disassociated by ultraviolet light, but its residence time is very short. And that's why we get these really, I think what happens, you get that dissociation of the methane, you get a spike in temperature, but immediately that methane in the atmosphere after the dissociation of the clathrate, it's dissipated by ultraviolet light, so it begins to cool right away. So what happens? Most of this carbon and almost all of the CO2 on the surface of the Earth is in limestone. It's not in you, it's not in plants, it's not in the atmosphere. The atmosphere has the lowest concentration of CO2 versus water. I showed you the concentration, how it increases in water with respect to pressure. And so one of the most abundant of the metals, or the couple of very abundant metals, are on that little list that you have passed out. If you look down through that table, you'll see two elements, calcium and magnesium. These are much more abundant than carbon. And it's those two elements that form carbonate minerals. The dominant carbonate minerals are calcium carbonate and magnesium carbonate. And so any calcium or magnesium in water, and if you go home and look in your toilet bowl, you'll probably see, if you have a water well and you don't not on city water, you'll see a little ring around the collar. And it's a white ring generally, or sometimes it's a little yellow because of the iron in it. But that calcium-rich water is sucking CO2 right out of the atmosphere and producing limestone in your toilet. That happens in the soils. It happens in the rocks, like I mentioned, in the mid-ocean ridges. And thus, the CO2 is being constantly taken out of the atmosphere that we generate. And because it really doesn't make any difference how much CO2 there is in the atmosphere as affected temperature, out here where we are now, we're looking at temperature effects that are less than 0.5 degrees centigrade. Well, all of these other forcing mechanisms have a much greater impact on the temperature than 0.5 degree centigrade. And we saw that with all the data with respect to oxygen isotopes over the periods of the ice ages.
So there's gonna be a test of this later, so.
Later, right now, take out your paper.
So I wanna know, so taking all this data, all this information on the temperature change, Jeff Cook kind of tracks when the ice goes out of Harding Lake. So when's the ice gonna go out of Harding Lake?
In about 50 years, maybe never. If I was making book in Vegas, I'd bet on global cooling and not on global warming. The ice ages are only about 10,000 years long. Ours started in earnest about 11,500 years ago. So we're overdue.
You know, one point you mentioned before is that, you know, some of the weather they're having down the lower 48 sort of coincides with,
Oh yeah.
you know, the former ice sheet that, so we may be entering a period of ice age.
Yeah, if you look at the deflection of the polar vortex the last couple of years, Lake Superior froze over twice, or nearly twice in the last decade. And if you look at radar images of the polar vortex, many times over the last couple of winters, you could lay a geologic map of the extent, the maximum extent of the continental ice sheets, and it would just be mirrored by the extent of the polar vortex. It's like the polar vortex was focusing right on those terminal moraines of that ice sheet. And it will be there again someday in the future.
Yeah, what's interesting now, if you've seen the news, you know, New York State and New England is having snow. Even the Carolinas, I guess, are getting some hail. And, you know, that's been kind of unusual.
Yeah.
So my mom lives down there, my family is on the Atlantic. And what I can tell you is the weather is weird. When I was a kid.
The weather's weird?
It's weird. When I was a kid, we got snow. Not a lot. It didn't last forever like it does up here, but we did get snow. I mean, I remember having nice sledding days and snow days. And here in the last the years have progressed, there's fewer and fewer of those. But they got dumped on in July. You know, my aunt was coming down from New Jersey, and they had to pull up on the side of the road for a blinding snowstorm in July. which within an hour had warmed back up to 80 degrees. So I guess I'm kind of digging on this, but I guess I'm resistant to implications that things aren't happening, because they are. I go home regularly. I can tell you that yes, I have changed. My body has changed. I'm an Alaskan. The heat is different. It is different than it was when I was a kid. That mugging you talked about, well, now it's like a direct radiant heat. It almost feels like Arizona sometimes when I go home. And that's not the way it used to be.
You don't have the advantage, Jomo, of being able to go home over, a million-year period, so you don't really have anything to compare with.
I only have a lifetime. I only got 20 years of experience.
There's indications in some of the older polar ice core data for the earlier advance, for the avian, the Illinois and ice advance, that may have occurred over as short a period as 3 years.
Well,
Very, very cold temperatures, just the bottom just dropped out. And
my whole point is, so what? So what? It's been changing, as we've seen, both short-term and long-term. Climate has been changing forever.
I'm not as blithe about it as you.
Yeah.
That's all. I'm just not as blithe about that.
well,
I'm personally, again, I saw this, and I saw some of the tracking you're talking about, how heating periods are followed by cooling periods, and we're not sure about the mechanism as far as what actually kicks off these ice ages, what kicks them off, and then what makes them subside again.
You're more enamored, Jumbo, of what man can do to change the climate than what nature can do.
What I know is that the Sahara Desert, the Sahara, which just means desert, we did help make that, and it was some of the clear cutting that the Romans did. Now there were some climatic things. Oh yeah, there were some climatic things that were happening. We're accelerating, exacerbating, but there was also some human impact. And I guess again, I'm not as blithe about our ability to alter the world, considering that I'm sitting in a room with guys whose whole bailiwick was altering the world. Who now on the back end want to act like you couldn't fucking do anything. So I know.
Joe Mo, in a 10-year period, in the late 90s, in a 10-year period, the National Science Foundation spent close to $30 billion, about $3 billion a year in grant money, trying to prove that humans were the cause of global warming. Instead of putting that $30 billion to good use in determining how their engineers and scientists could ameliorate the problem of global warming, because it's going to come regardless of human beings. We have history of this.
No, again, for me, it's just where I believe there's good evidence we're a contributing factor. I don't, being a contributing factor, question is, what do we do about, how do we modulate our contribution?
Even if I agreed with you, even if I agreed with you, how often do you see in the literature on global warming, you ever see what is presented in that first dot up there on volcanism, on Earth's orbit around the sun, any of these things that have a huge influence on global warming? You never see that advertised as any part of global warming. It's always what we can do to ameliorate or reduce carbon dioxide and fossil fuel.
I'm sorry, but I spend too much time trying to develop fossil fuels at the same time I'm trying to develop alternate energy. You know what I do for a living.
Well, thank you, Paul. It was a
Good, great presentation.
very good presentation. And, I think that we are at a stage in our lifetimes where you can't produce enough evidence to convince some people of what reality is.
Yeah.
And we have an example in our midst.
Well, our environmental friends didn't show up, so I figured I had to.
Yeah.
Hey, Mike is one of the leaders in global warming.
Will we be able to get a copy of your slides?
So, yeah, Jomo's got,
I've got them.
Okay.
Well, have you got this? Oh,
Uh-huh.
great, good, Jomo.
I will try to, I think it's like 10 megs,
yeah, it's pretty big.
but I'll give it a shot. I'll try something
I
else.
can't, I couldn't bring up that one I did. It's that, I've got to get into some program that I couldn't bring up on my computer.
You're PDF on YouTube?
Yeah, you could, if you could just, you know, you got a PDF of that, so you could just email it.
Sure.
Now, you might do a PDF on that. I can do that.
Okay. Oh, yeah, I've got, in fact, it's already PDF, but yes, so I see you two would like it, so I'll make sure it goes out. And I'll post the video also. I do have a question. I shouldn't say this in front of the boss, but I don't actually have anything lined up for next week. Is there anybody, I was gonna try to reach out to Alice Edwards. She's the one, Deputy Commissioner, Air Quality. They're gonna be doing the presentation at the chamber for the luncheon today. And I was gonna see if we could get her to at least call in and give us a more intimate discussion on that SIP for next Tuesday. I'll give it a shot.
Mm-hmm.
Otherwise, I might give you guys the week off if Mr.
You guys can come out in the field with me on Monday next and stay out there for the week. Come for having presentation.
You got steaks and.
You better have a warm sleeping bag, because it's pretty damn cold out there.
Yeah.
Oh,
I've been out there.
I put one more thing on everybody's radar. The HB87 for LNG storage reimbursement did leave House Finance this weekend. It's supposed to be acted on the floor and moved to the Senate, but we don't have a whole lot of time. So if everybody could just kind of be on deck and ready if we need folks to call in or testify, because we don't have a whole lot of time to try to get to the Senate. I mean, we have like very little time if they don't do an extension.
What's your assessment, Jane?
It's in third reading today, on the floor. So whether it gets reconsidered by the minority to drag it one more day, which would almost be the kiss of death. I'm not sure what, Senator Bishop may try to line up on the Senate side. I thought maybe I'd try and call Erie today or something like that, or see if he, I don't know, is there an idea of at least work session today?
No.
No meeting today? Because I thought there might have been an update. Yeah, it's very tight on time, but things can move quickly at the end if it's all worked out.
Okay, well, thank you, everybody. Thank you, Ken.
Thank you. Yeah.
Very good.
I appreciate that.
Jomo, I want you to understand, I'm a firm believer in climate change. Been changing up and down for years. Not gonna stop.
Well, before the
I just feel like
coming of man.
I feel like if there's a problem and I'm a contributor to a problem, even if my contribution is minimal, you know, is that an excuse not to try to adjust whatever I'm doing that is contributing to a problem?
But don't you have to balance that against other social standards, including the economies? You have to balance those perceived needs against other things that are not perceived. We know how much it's going to cost to live. We know what our social structures are and how it could disembowel those social structures. We have givens, but in certain other things, we don't have a given in this climate thing. We all know, or we should know. I don't adhere to the principle that some people say, oh, there's no climate change. Well, there is climate change. There is climate change. And it may not be deleterious. It may not be as catastrophic as has been presented here, as some people believe, but there's climate change. And there's short-term climate change. I agree. But you got to balance those things. How you address those climate changes has got to be balanced with some common sense on what it's going to do to society and what it's going to do to the economy of those societies.
Again, you know, I'm the guy trying to do the balancing act.
Well, that's good because you've got some common sense. But there are people that don't. They're just saying let's completely eradicate everything and
there are zealots
in favor of
There are
climate.
zealots in
Ameliorating
all
climate
things of all stripes. And if there's one consistency across zealotry, it's the hyper focus on whatever it is they're interested in to the exclusion of other considerations. It's kind of like the hallmark of zealotry.
But there's also the Pavlovian principle that repetition we'll use the new modern term, brainwash people, and that's what has been happening, repetition, starting with Gore, not starting with Gore, but Gore being a principle of it, until everybody begins to believe an untruth.
But it didn't start with man. Folks been doing that for a while too.
That's one I know.
Conditioned reflexes,
Conditioned reflex.
conditioned